All right, well, let's continue. So next I'd like to talk about electron pairing. So this is very mysterious when you think about it. I mean, electrons repel each other, right? So how can two electrons form a pair? Well, here, let's take a look. Here are my two electrons. Okay? Of course, in vacuum, electrons do repel. But inside of a conductor, we already know that the electric field of each electron will be strongly screened. We talked about Thomas Fermi screening back when we began to talk about electrons in a metal as a quantum gas. That is, the other conduction electrons in the material rearrange themselves to try to cancel out the electric field. Okay? In addition, the other charges in the material, the lattice ions, will themselves rearrange slightly around the electron because those positive charges are attracted to the negative charge on the electron, and that also screens the electric field. And what I'd like to show you is that under some cases, this screening can even produce a slight residual attractive interaction. This doesn't occur in the static case when the electrons are motionless, but it can occur when the electrons are moving. I think it's easiest to show you this with some cartoon pictures, which I'm going to share in a PowerPoint. 1 second. Here we go. So first, let's consider a static electron inside of our metal. Here's the electron, and here are the positive ions around it. Of course, the negative charge on the electron attracts the ions, and we get some lattice distortion around this. Sometimes this combination of charge and lattice distortion is called a polaron, but we don't need to use that name. We can also think of this lattice distortion as being, I don't know, it's composed of a superposition of phonon states, since phonons describe lattice distortions and lattice vibrations. In any event, there it is. Now, this is the situation when the electron is static. What happens if the electron is moving? Well, so again, when the electron is static, we have a negative charge, but due to lattice polarization, we have this cloud of excess positive charge in the vicinity of the electron. So that was the screening effect. But when the electron is moving, something interesting will happen. The electron is very light. It moves very fast. Imagine an electron at the Fermi energy. So it's moving with the Fermi velocity, very, very fast. On the other hand, the ions are heavy, and so they may lag behind the electron. The lattice distortion may lag behind the electron. Here's the picture, okay? So here's my electron moving through the material, and here's the lattice distortion, which is lagging behind because the ions are heavy. They have a lot of inertia, and they can't quite follow the distortion. I'm sorry, they can't quite follow the electron perfectly. Of course, what this means is that there's a cloud of positive charge that's trailing behind the electron in this picture. Okay? So that's the essential element. If I have moving charges, 1 second. If I have moving charges, one moving charge may interact with the positive cloud that's trailing the other moving charge. In a picture sort of like this. Here are my electrons now moving. And here's the cloud of positive charge that's trailing the first electron. And the second electron can be attracted to this positive charge, and that produces a net attractive interaction between the two electrons. Well, it's kind of an interesting idea. This is a qualitative picture. Here's the charge trailing the second electron, but it gives us an idea how an attractive interaction can result when electrons move through a solid. Okay. Now, there's another way to describe this. Once we know that we can have this attractive interaction, then we can describe the interaction using pictures like this, like Feynman diagrams. Imagine I have two electrons, and they can interact by exchanging a phonon. In these drawings, phonons are usually drawn as this kind of spiky line here, okay? And something that drops out of this picture is that the exchanged energy, the energy transfer from one electron to another in this interaction, must be less than or equal to the energy of the photon. Well, it must be equal to the energy of the photon. And so in particular, it must be less than or equal to the energy of the most energetic photon. The frequency of the most energetic photon is called the Debye frequency, or omega sub d. So the exchanged energy must be less than omega sub d. And this leads us to another picture. Okay? And that looks like this. So this picture, I'm going to draw the density of states for the electrons in a conductor. With density of states on the x-axis and energy on the y-axis. And we know what the density of states looks like for a free electron gas. All the states up to the Fermi energy are full at low temperature, and the states above it are empty. So what we found out now is that electrons can interact with each other through the lattice distortion. That is, electrons can interact with each other by exchanging phonons. But the energy exchanged in the interaction is limited to the energy of the most energetic phonon. And that means that in this picture, not all of the electrons pair with each other. It's only those electrons that are within h bar omega d that interact. And so it's only in this region, these are the electrons that exhibit the pairing. And so it's only this part of the density of states that becomes distorted. And as a result of the interaction, the density of states is reformed. To show a gap. We drew this picture last time, but it results from this pairing interaction. And the size of the gap to delta is related to the strength of the pairing interaction. In particular, BCS theory says that the size of the energy gap is proportional to h bar omega d, okay? The energy of the most energetic boson.